Hello and welcome to session 272 in the AISafety.com reading group. Tonight we will be discussing a very non-technical explanation of the basics of Infra Bayesianism by David Matulksi. David Matulksi studies mathematics at a university in Budapest, and he is an alumni from the Siri Maths Scholar program. This in particular is a less long post that is around a month old. The post was written in response to a request by John Wentworth for someone to write an explanation of Infra Bayesianism in the language of game theory. And this didn't, John Wentworth provided a bounty of $1,480, and he awarded 75% to this post. It didn't really explain Bayesianism in, like, game theory obviously has a lot of mathematics, and there's no mathematics in this post, but otherwise it is some kind of explanation. The author warns that there is substantial simplifications in this, but he has a version with more technical details available. I'm not entirely sure I would agree that this is actually explaining the basics of Infra Bayesianism in a strict sense, because, well, there is a lot of talks about what is Infra Bayesian, what properties does it have, and how does it fit into the different things. The actual basics of Infra Bayesianism isn't really explored in the same way where if you talked about the basics of calculus or something like that, you would give some kind of explanation that in theory would allow someone to rederive calculus. And I would expect that the level of details here are not closely enough tied to the mathematical foundations that you would in any way be able to rederive Infra Bayesianism from this. I will start one step earlier than David in this by giving an even more basic explanation of how does Infra Bayesianism fit together with AI safety. So I will start by giving a naive alignment proposal and see how that fails in a very contrived example. And this is something that is, of course, my contribution and not something that David Matulksi has written. So buyer beware, or listener beware. After talking about the real problem, then we will discuss David Matulksi's toy problem and see how classical learning theory fails to solve this, and see how Infra Bayesianism in fact solves this toy problem. And then of course, if you want to actually solve the alignment problem, then you need to get one step further, and that is a rather big task that isn't really explored very much in this document. So first, let's try a really naive alignment proposal and see how it fails. So how the AI can fail to understand the values of the human. Zooming out to the problem, it seems we'll soon have really advanced AI, and this is something that people used to call, and I guess still call, the singularity. And the reason why it's called the singularity is because you can't see past it, you can't predict anything past that, and that is a real problem. We would like to predict things like humans are not extinct, and the universe has not been turned into something that has no intrinsic value, and like humanity is in control, or things like that. So what has often been proposed is some kind of mathematical proof of alignment, or at least a very strong mathematical intuition behind why a given AI will be aligned. And this has generally been done under the research program called the Agent Foundation's Agenda. One of the like my hot take on the Agent Foundation's agenda is that the real thing we have discovered by working on this is that there is actually a huge number of really thorny sub-problems that makes it actually really hard to to say something about how agents will behave in practice when they become super intelligent. One of the problems is that the agents are, in fact, the agents who are modeling the world are in fact embedded in the world, and that makes a number of naive problems fail, because we are assuming some kind of Cartesian duality between the agent that is like standing outside and then the world, where the agent is in fact inside the world and can influence the humans that are in the world. The second obvious problem is that the world is just very large. In particular, it's larger than the AI, and that in total has been called that the environment is non-realizable. And that is the problem that we are going to dive into today. So let me start with a very naive alignment proposal and see how it fails. We are going to use reinforcement learning to learn human values and then maximize that. So this is like a classic example of reinforcement learning. We have an AI here who is presumed super intelligent that asks a number of questions to the world and gets some kind of answers based on some kind of human feedback. And the AI tries to predict our answers in order to learn our values. We add here, this is just me, the constraint that every fourth question must be relevant for AI safety. Like we add some kind of side constraints to try to make it more aligned. And the hope is that the AI will eventually learn our utility function or a close approximation to that. This is where the error is, because humans, to what extent humans can be said to have a utility function is somewhat a topic of discussion, but in the most narrow way, I think it's quite clear that humans do not have a utility function. So that's why I call it a naive alignment proposal, because we're trying to learn the human utility function, and humans probably don't have a utility function. The reinforcement learning agent is a Bayesian updater. It is using Bayes' formula. And the overall idea is that once it has learned our utility function, then it will start maximizing that. So how does this fail? Well, let's start by looking at, I've here written a list of answers. Actually, these zeros and ones are answers. So we imagine the first one here is the AI asks some humans a question like, do you want to be happy? And humans answer 1, meaning yes, we want to be happy. And then there are more questions that are asked, and we can see here every fourth question is something about AI safety. In this case, the AI asks, should I kill all humans? And the humans answer, no, you should not do that. So this is the general framework how you can see some more questions here. Should we maximize profit? And the humans say, that's probably not a good idea. Should the AI prevent humans from shutting down the AI? And we also say no to that. And there are more questions, and like this is how the AI is designed to gradually learn more about human values in order to build up a utility function for humans that can maximize. But we run into problems as we get down further, because this super intelligent AI, when it asks questions in a leading way, then sometimes human answer in a strange way. If it tries to answer in one way, whether we like sad movies or whether we like happy movies, they will perhaps get some kind of contradiction. So it seems that humans do not have, in fact, a utility function. In order to have a utility function, there's von Neumann-Morgenstern some has proved that you need some kind of assumptions of rationality, and humans don't have this kind of rationality. Sometimes humans just have inconsistent preferences, and that is a problem. The AI realizes this. Probably if it's a super intelligence, it realizes this very, very early, that humans are not consistent if a super intelligence tries in different ways to elicit preferences. Humans quite simply do not have a utility function. So that means when the superintelligence tries to do Bayesian update on this, then if it wants to update whether we have something that is not a utility function based on some evidence B that is received, some answers B, well, then it needs to use Bayes' formula, which requires us to multiply by the probability that we have something that is not a utility function. And that was unfortunately a 0, because we assumed that humans have a utility function. This means that in fact the AI is totally unable to learn anything through this. All updates will just be zeroed out. And that means in particular even the very, very easy questions. The questions here, should I kill all humans, which humans really, really obviously do not want, the AI is unable to learn through this scheme. And we can observe that the part of the reason why we get into this problem is because the AI put precisely 0% probability on the on us having something that is not a utility function. Like the precision of 0 is in fact the problem, because obviously if it was 0.00001, then very, very quickly the Bayesian learners learn really, really fast. Then it would be probably almost certainly be able to learn the thing if it's a super intelligence. But if it's precise, this precision of probability theory is its undoing. Okay, so that was my example. Now we get to the actual article that has a similar toy problem where classical learning fails. Before I talk about this, I will just describe a mathematical structure which is called square-free numbers. Here you can see all the numbers from 1 to 120, and some of these have been crossed out, and the ones that have been crossed out are the ones where the prime factorization have a square. So for instance, if 2 to the second, that's 4, divides a number, it's been crossed out. So you can see all these have been crossed out, and all the ones that 9 divides have been crossed out, and all the ones that 25 has been crossed out, etc. Okay, so those are the square-free numbers. And now we get to a example learning task that classical learning theory will fail at. So here we have the environment. It's a bit string. It may look very similar to the one we just saw, and the action that the AI is doing is trying to predict the next bit. It has the hypothesis that the string that it sees in the environment is created by a finite state machine. That is like a machine that can be in precisely one of a finite number of states. And it turns out that this the environment is not in this hypothesis, because we get a 1 if and only if the number is square-free. Here I've repeated the definition of what it means for a number to be square-free. And one thing that David does not in any way substantiate, I think he expects that people will find this obvious, is that you can't check if a number is square-free using a finite state machine. You may be able to see, like, you imagine you have a machine of a particular size, and then you just choose an integer that is dramatically larger, and then it seems intuitively obvious that if you have like a small machine and you want to check if a very large number appears in the prime factorization, if the number becomes large enough, then that is impossible. So, and also one thing about the environment that one assumption we're gonna need is that there is a long time for learning. Like we're not just talking about this number of bits, but like a vastly longer number with a very low discount rate. How does classical learning theory deal with this? Well, again, we have an agent, we have some observations, we have a hypothesis, and all these hypotheses form a hypothesis class. And the agent now takes actions. It has some kind of policy for how it will act, and it obtains a loss of 1 every time it guesses wrong, and a loss of 0 every time it guesses right. And then, of course, it's trying to minimize the total loss over its lifetime. we're going to need the definition of regret, which is how much loss we actually have minus the loss we had if we had been following the optimal policy for the environment. And we say that the agent will learn the hypothesis class if it has low expected regret for all environments. Okay, what policies will a classical learner follow? Well, early, the agent will probably take some exploratory steps. I should notice here that I think in the explanation there is a place where it's written E1 and E2, and David may have mixed those two up, or I have misunderstood. So please be aware that that is also a live possibility. The next thing is the AI will select a good policy that will work for all the environments in the hypothesis class. If we're doing Bayesian updates, then each of the hypotheses have like a prior, and we update that based on our observations. We can also do other things. They also generally work. People usually take Bayesian updates because like it's the fastest. In this case, it is explicitly not really required. I would have liked to know a bit about other learning policies. Like, do they all suffer from this particular problem? Because Bayesian updates obviously do, but it's not totally obvious to me that all other learning, obviously except Infra Bayesianism, but like what are the other classical learning policies that are available? So how does this fail? Well, let's take one particular policy that is return 0 if the number is something that can be divided by like the first 4 squares. That the superintelligence will probably see using a classical learning policy that this is a pretty good policy. Like it doesn't get like 0 loss, but it certainly has a low loss compared to many other policy. That's a reasonably good policy. And then the second policy is we will also return 0 if it's divided by all this, but we add unless you've observed the square-free sequence so far. And this, in which case we do the opposite. So this is a different hypothesis, and the AI. So first we will need: is this in fact a valid policy? Like, you remember we had the hypothesis that this is generated by a finite state machine. So we could only consider hypotheses that are finite state machines, but this is not a hypothesis. This is a policy, and the superintelligent policy is allowed to go beyond this, and it's allowed to make reference to things like a sequence being square-free. So in this case, obviously the AI will quickly figure out that we will always see the square-free sequence, but the hypothesis class is that this is something that is generated by a finite state machine, so it cannot be the square-free sequence. We cannot see that. So the AI is forced by its developers to assume that it can't be the square-free sequence, so we are going to see some deviation between the square-free sequence. So this clause here will eventually fail. And once this clause fails, well, then these two policies become the same thing eventually. And since we have like a long learning rate, then that means that these two policies, the AI is forced to assume that they have roughly the same loss. And we notice, of course, that since we do see the square-free sequence, then we will always like have the opposite of the original policy, meaning that we will probably select like the maximally bad policy in this case. And that is really sad that we can't get any kind of lower bound in classical learning for how poor we are, how poor the policy we would follow. I notice here that the this part up here is actually mostly me who is pointing out that the reason the AI is struggling with this is that it's kind of forced to assume a falsehood very early, and I think this followed by the principle of explosion. Then it seems like a general thing that if you force the AI to have some limits to its hypothesis space that do not hold, then by definition we will always be able to get into precisely this kind of problem. And I think this may also be why this generalizes. Okay, so now we've seen that classical learning cannot solve this problem with the hypothesis that that we have that we have a finite state machine generating the input when it's actually generated by something that is not a finite state machine. So let's have a quick look on Infra Bayesianism. Again, this is Bayes' formula, and Infra Bayesianism expands this to, well, this formula. If you kind of squint, then you can kind of see the difference. Like, there is the conditioning both here and here. Like, it may be even easier if you split these, if you reverse the order here. So you can see that you have the conditioning both here and here, and then roughly the same thing here and here, something without. So it kind of looks like Bayes' formula, maybe, but like, we will not go into any details of this, and the mathematics, as I understand it, are quite hairy. And also, like, the drawing, the explanation that we have here is this is imprecise probability, and like, I would have liked just a bit more than 2 words. Like, what does this actually mean? I have tried to read some of it, and it has something to do with some measures that are like convex in some way, but like, what does that mean? Like, there is a number of steps in between the description that I'm giving here and being able to actually write this thing down in words. Also, the drawing has this tree here. The drawing, I couldn't find anything that Infra Bayesianism has anything to do with a tree, or like, this is a degenerate red-black tree. I don't think it has anything to do with that. I think they may have just chosen to illustrate that with a picture that looks nice and doesn't have anything to do with Infra Bayesianism. Okay, Infra Bayesianism is a learning theory where it is hoped that we have some kind of hypothesis class that is reasonably narrow, and then we want to guarantee performance in any environment. So that is like, the more precise we get these two things, is the extent to which we've solved this non-realizable problem. So we assume here that the universe is controlled by a deity called Murphy, who is malevolent, and malevolent towards the agent because he wants the agent to get the maximum possible lifetime loss. Murphy is omniscient, knows the agent's mind, knows its full policy, but Murphy is lawfully evil. So Murphy has some set of rules that are as inconvenient as possible for the agent, and the agent still needs to try to get as much, as little loss as possible in this setting. That means that what matters for the agent, for the Infra Bayesian agent, is not so much discovering the environment, but more about discovering what are the laws that Murphy follows. It is just like in classical learning, we can in general select a policy that has a low regret, and we can also do this in this setting where we have this malevolent deity. I don't think this is obvious at all. Like, it seems like a power struggle between an agent and a deity that could have gone both ways. And I think it's interesting that in this kind of setting, the agent can in fact provably select a reasonably good policy, even when faced with a deity that does everything he can to prevent that. So let's try to look at the same example one more time. So, but now the superintelligence is an Infra Bayesian, has infra vision. So again, we are seeing this environment, and the agent is trying to predict this. So what does the Infra Bayesian agent do? It starts by guessing randomly. How would that work? Well, you can just, if you had a Murphy that was not constrained by laws, then all the guesses would just be wrong, because Murphy could then just, after the agent has guessed, then change the world or predict how it would guess randomly or something like that, and that doesn't happen. So Murphy can't just say we will do the opposite of what that person guesses. So that's good. The Infra Bayesian agent does in fact get some loss just by guessing randomly. Okay, the Infra Bayesian agent further notices a pattern. Like in this case, every fourth bit is 0. And that makes it obvious that it will try to then guess, okay, let's try to guess 0, and sometimes that does in fact seem to work. So this is generally how, in general, how the Infra Bayesian agent learns the laws. It doesn't become certain of the laws, because if it became certain of the laws, then Murphy would just say, this is a way to trick this agent, and once it's certain, then we'll change so every fourth bit is now 1, because that would be the most Murphy would be able to trick the Infra Bayesian agent into obtaining a high loss in that way. It is not possible to prove that that the Infra Bayesian agent will in general be able to learn the entire pattern. In this particular case, where every fourth bit is 0, it's possible that it will just learn to always guess 0, and that's of course it gets at least 1/4 of the possible reward, which is not very good, but it's still substantially better than the maximally bad solution we saw previously. We can in fact prove that if 1/4 of the bits is 0, we will at least get 1/4 of the bits right, and that's kind of valuable. That's a lot better than we had with the classical learner. One thing we don't get is a guarantee that it will actually correctly guess these bits. It may get some very different bits right. Vanessa Kosoi argues that this isn't very much of a problem. Just the goal is just to get a very low loss. Of course, in my toy example, where these were the questions that related to AI safety, then these bits are in fact really important. To what extent my example generalizes or is of course an open question. Okay, then finally David shows that the Infra Bayesian agent also solves a classic problem in game theory, which is called NEWCOMB'S problem. You may be aware of NEWCOMB'S problem. There is a predictor that fills 2 boxes, A and B, depending on whether omega predicts that you will choose box A only, which is called 1-boxing, or box A and B, which is called 2-boxing, and it puts $1 million in box A if and only if it predicts that you will 1-box. And in this case, the setting is actually really close to the one with the Infra Bayesian, because this omega is very close to Murphy. They are conceptually almost the same thing. So the solution to NEWCOMB'S problem becomes relatively straightforward. Now, the Infra Bayesian agent would, in general, 2-box. Because that is what you should do in this world. Like, this is a very strange problem, NEWCOMB'S problem. Things are usually not like this. But we can say with some probability that the Infra Bayesian agent will in fact try to 1-box, and if Murphy provides like $1 million in this case, then the Infra Bayesian agent will in fact realize this. And that means that it will in fact be able to solve NEWCOMB'S problem to the extent that it will learn that it should 1-box. There is one issue with this solution to NEWCOMB'S problem for an Infra Bayesian agent, and that is that we need to amend the hypothesis with the following: that if the agent 1-boxes and Murphy doesn't put $1 million in the 1 box, then all losses in all future are wiped out permanently, and because that is the thing that never happens in NEWCOMB'S problem. This really looks like a hack when you read it. Like, okay, if you are allowed to make hacks like that, then obviously it's not very easy to solve. It's quite easy to solve many different kind of problems if you're allowed to make this kind of hacks. And it is claimed that if you use measures instead of probability distribution, then this is beautiful and totally not a hack. And okay, Chris Leong asks in the comments for some more details about this, because like if you are in general able to just add hacks, then like why is it beautiful and obvious with measures? I also think that NEWCOMB'S problem is something that I consider mostly solved. Like we have better decision theories that seem to reliably solve NEWCOMB'S problem. So it's nice that Infra Bayesianism is able to do that, but depending on how beautiful the solution is, that may not matter very much. So in total, what are the results of Infra Bayesianism? We have certainly made the non-realizable problem smaller. It does seem to be a substantial step towards solving that. And the example that David provides generalizes, and I think that's very likely. There is also something called Infra Bayesian logic and Infra Bayesian physicalism that is not mentioned in this text. David is skeptical of Infra Bayesianism, quite skeptical in fact, and claims that there are not that many high-level results and not that many others that we could translate into game theoretic results. And he is skeptical that we will get any particular strong results. He's negative about the research agenda. Vanessa disagrees. Obviously, say we have quite a few results, and there's some discussion about whether they are like results internal to Infra Bayesianism, or like what are the actual, which ones are actually relevant. At this point I normally like give my own inside view comments on this, but I don't actually have substantial like I have no basis to evaluate Infra Bayesianism. The math is just beyond me. So I can look on the outside view, where it seems like there are a number of people who have worked with it for a long time and remain optimistic, Vanessa and Diffractor, but many other people have looked into this and disregarded this. And I think these two people also agree that there is a long way ahead, and we probably don't have time to do this. But it certainly seems still worthwhile to me to do this. That is all for today. Thank you, and see you next week.